Hello, in this lecture we'll find out the area of the green shape using two different methods. In the drawing we have two circles. Each circle is passing through the center of the other circle, and we know that the radius of each circle is equal to 5 units, and we want to find out the area of this green shape. So we start with the first method, and first of all I will explain to you what is a sector. A sector is the area inside a circle that is bounded by two radiuses and the arc that is located between those two radiuses. Here, this green shape is sector AOB, and the formula for the area of this sector is pi r squared times the angle between those two radiuses over 360 degrees. In this case, the angle between the radiuses is 60 degrees, so in this case the area will be equal to pi r squared times 60 degrees over 360 degrees, but the angle between the two radiuses could be any other angle, and we will multiply that angle by pi r squared, and we'll divide it by 360 degrees. So the area of this specific sector equals to pi r squared times 60 degrees over 360 degrees, when r is the radius of this circle. Okay, and the second term is sector, and sector is the area that is bounded between the chord AB and arc AB. Okay, so the area that is bounded by a chord and the arc that is attached to that chord is defined as a segment, and the formula for a segment, the area of a segment equals to the area of sector AOB minus the area of triangle AOB. If you subtract from sector AOB the area of triangle AOB, you will get segment AB that is actually this green shape. Okay, again, the area of a sector equals to the area of a segment equals to the area of sector AOB, in this case, minus the area of triangle AOB. It will be equal to the area of segment AB. Okay, and so we will define the center of this circle as point P, and the center of this circle as point Q. We will define the intersection point, the first intersection point between those two circles as point A, and we will define the second intersection point of those two circles as point B. Then we will join together points P and B by a straight line, here PB is the radius of this circle because of the fact that it starts from the center of this circle, that is to say from point B, and ends at point B, that is a point on the circle itself. Therefore PB is the radius of this circle, that is to say it equals to 5 units because of the fact that we know that the radius of each circle equals to 5 units. We join points Q and B together by a straight line. Line segment QB is the radius of this circle because of the fact that it starts from the center of this circle, that is to say from point Q, and ends at point B, that is a point on the circle itself, on this circle itself. Therefore it is the radius of this circle, that is to say it equals to 5 units. We join points A and P together by a straight line. AP, line segment AP is the radius of this circle because of the fact that it starts from the center of this circle, that is to say from point P, and ends at point A, that is a point on this circle itself. Therefore AP is the radius of this circle, that is to say it equals to 5 units. And we join points A and Q together by a straight line. So AQ, line segment AQ is the radius of this circle because of the fact that it starts from the center of this circle and ends at point A, that is a point of this circle itself. Therefore it is the radius of this circle, that is to say it equals to 5 units. So here we have quadrilateral APBQ. In quadrilateral APBQ, all of its sides are equal to each other. All of its sides are equal to 5 units. Therefore, quadrilateral APBQ is a rhombus. So I'll write it down. Quadrilateral APBQ is a rhombus any quadrilateral that all of its sides are equal to each other is a rhombus, except from a square if all the sides of a quadrilateral are equal to each other, and also all of its sides is equal to 90 degrees, then it is a square. But here the angles here are not right angles, therefore it is not a square but a rhombus. Okay, and we will join points A and B together by a straight line. AB is the first diagonal of rhombus APBQ, and we will join points P and Q together by a straight line. PQ is first of all the radius of this circle because of the fact that it starts from point P, that is the center of this circle, and ends at point Q, that is a point on this circle itself. Therefore it is the radius of this circle, that is to say it equals to 5 units. So I'll write it down that PQ equals to 5 units as the radius of this circle. here we will define the intersection point between diagonal AB and diagonal PQ of rhombus APBQ as point M. And the diagonals of a rhombus, that is to say AB and PQ, has two characteristics. I will write them down. The characteristics of the diagonals of a rhombus the first characteristic of the diagonals of a rhombus is that they are perpendicular to each other. So here the diagonal AB is perpendicular to the diagonal PQ, and the diagonal PQ is perpendicular to the diagonal AB. That is to say, we will have here four right angles. Okay, and the second characteristic of the diagonals of a rhombus is that they bisect each other. They bisect each other. So here the diagonal AB bisect diagonal PQ, that is to say PM equals to MQ, and the diagonal PQ bisect diagonal AB, that is to say AM equals to MB. So PM equals to MQ. So if we define PM as X, then MQ will be also equal to X. And X plus X equals to PQ. X plus X equals to PQ, but we have already found out that PQ equals to 5 units. So x plus x is 2x, and 2x equals to 5. Here we will divide this equation by 2, and we will get that x equals to 5 over 2 units. So here we will substitute x by 5 over 2 units. That is to say Pm will be equal to 5 over 2 units. And here mq that equals to x will be also equal to 5 over 2, so we substitute x by 5 over 2. And in the next step, we will focus on triangles APM, the right triangle AMQ, the right triangle MQB, and the right triangle PMB. We will focus on those angles, those 4 angles. Actually, the cosine of those 4 angles, but first of all, I'll write it down that we will focus on the right triangle APM. We will focus on the right triangle AMQ. We will focus on the right triangle PMB. And the right triangle MQB. So actually, on those 4 right triangles, we will focus on the angles that I marked here, and the cosine of those 4 angles in those 4 triangles. The cosine of those 4 angles will be equal to 5 over 2 over 5. I will repeat again. The cosine of the 4 angles that I marked in those 4 triangles will be equal to 5 over 2 over 5. So here 5 over 2 over 5 equals to 5 over 5 times 2. 5 over 5 is 1. So it is 1 over 2. So we found out that the cosine of the 4 angles that I marked in those 4 triangles equal to 1 over 2. And if cosine equals to 1 over 2, it means that the angle itself must be equal to 60 degrees. So all the 4 angles are equal to 60 degrees. So we can write here that this angle equals to 60 degrees. This angle also equals to 60 degrees. This angle equals to 60 degrees. And this angle also equals to 60 degrees. Okay? So in the next step, we will focus on those 2 triangles, triangle APB and triangle AQB, and we'll prove that those two triangles can go into each other. So I'll write it down. We will focus on this triangle APB, and on this triangle AQB. And we will prove that those two triangles can go into each other. Why those two triangles can go into each other? First of all, AP equals to AQ equals to 5 units. AP equals to AQ equals to 5 units. I'll repeat again. AP equals to AQ equals to 5 units. And also PB equals to BQ, and they're also equal to 5 units. PB equals to BQ, both sides are equal to 5 units. PB equals to BQ, and they're both equal to 5 units. And AB, side AB equals to itself. It is a common side that belongs to both triangles, so AB equals to AB is a common side that belongs to both triangles. I will repeat again. AB equals to AB is a common side that belongs to both triangles. So actually we proved that those two triangles can go into each other according to side rule. So I will write it down. Triangle APB congruent, this is the sign of congruent, to triangle AQB according to side rule. Okay, we actually found that all three sides of triangle APB can go into all three sides of triangle AQB. Therefore, those two triangles can go into each other according to side rule. And from the fact that those two triangles can go into each other, we will conclude that they have also the same areas. So, therefore, we can write down that the area of triangle APB, here the square bracket is the sign for the area. It means the area of triangle APB is equal to the area of triangle AQB. Okay. So I write it also here that the area of triangle APB is equal to the area of triangle AQB. Okay. And what is the area of segment APB? Or what is the area of sector APB? The area of sector APB the area of this sector APB equals to pi r square times 60 degrees plus 60 degrees is 120 degrees over 360 degrees. I repeat again, the area of sector APB equals to pi r square times 120 degrees over 360 degrees. R equals to 5 units, so R square is 5 square, 5 square is 25. So here in the numerator we have 25 pi, and 120 degrees over 360 degrees is 1 over 3, so in the denominator we have 3. So we found out that the area of sector APB equals to 25 pi over 3 square units, and here we found out that the area of triangle APB is equal to the area of triangle AQB, so we will define the area of those two triangles as x. Okay, so the area of triangle APB equals to the area of triangle AQB, and they are equal to x square units. Okay. And what is the area of sector AQB? The area of sector AQB equals to pi r square times 120 degrees over 360 degrees. I will repeat again, the area of sector AQB equals to pi r square times 120 degrees over 360 degrees. R equals to 5, so R square is 5 square, and 5 square is 25. So in the numerator we have 25 pi, and in the denominator we have 120 degrees over 360 degrees is 1 over 3, so it is 3. And we found out that the area of sector AQB is also equal to 25 pi over 3 square units, exactly as the area of sector APB. So we can write down that the area of sector APB is equal to the area of sector AQB. This is one thing, and the other thing is that we have already found out that, so here the area of sector APB equals to the area of sector AQB, and they are both equal to 25 pi over 3 square units. And the second thing that we have already found out that is that the area of triangle APB is equal to the area of triangle AQB, and they are both equal to x square units. And what is the area of segment A? What is the area of segment APB? The area of segment APB the area of segment APB, actually it is the shape that it looks like a semicircle, but it is not a semicircle. The area of segment APB will be equal to the area of sector AQB minus the area of triangle AQB. I'll repeat again. The area of segment APB will be equal to the area of sector AQB minus the area of triangle AQB. Okay? That is to say, the area of sector AQB is 25 pi over 3, and the area of triangle AQB, according to our definition, is x. So in conclusion, we found out that the area of segment APB is equal to 25 pi over 3 minus x square units, and what is the area of segment AQB? The area of segment AQB here, the area of segment AQB, it is this shape that is look like a semicircle, but it is not a semicircle. So the area of segment APB, the shape that it is like a semicircle, it will be equal to the area of sector APB minus the area of triangle APB. Sector APB minus the area of triangle APB. And the area of sector APB is equal to 25 pi over 3, and the area of triangle APB equals to x according to our definition. So in conclusion, we found out that the area of segment AQB, that is 25 pi over 3 minus x, equals to the area of segment APB, that is also 25 pi over 3 minus x square units. So we can write down that the area of segment APB is equal to the area of segment AQB. Okay. And actually they are both equal to 25 pi over 3 minus x square units and what is the area of the green shape? The area of the green shape of this green shape is equal to the area of segment APB plus the area of segment AQB. And repeat again, the area of the green shape that we are looking for is equal to the area of segment APB, this segment, plus the area of segment AQB, this segment. But because of the fact that we found that the area of segment APB equals to the area of segment AQB, we can substitute the area of segment AQB by the area of segment APB. Why? Because they are equal to each other. So we do it now, and we will get that the area of the green shape will be equal to the area of segment APB plus the area of segment AQB, but we can substitute the area of segment AQB by the area of segment APB. Why? Because they are equal to each other in the areas. So we'll substitute the area of segment AQB by the area of segment APB. So it is plus the area of segment APB. So actually we found out that the area of the green shape equals to the area of segment APB plus the area of segment APB. That is to say, it equals to 2 times the area of segment APB. Equals to 2 times the area of segment APB. So it equals to 2 times, and we've already found out that the area of segment APB equals to 25 pi over 3 minus x. So the only thing that is left to do in order to find out the area of the green shape is to find out the value of x. Okay, to find out the value of x, and actually x is defined either as the area of triangle APB or the area of triangle AQB. They are both equal to x. So we will find out the area of triangle APB, that is x, and we will subtract 25 pi over 3 from x, we will multiply it by 2, and we will find out the green shape, the area of the green shape. Okay, so what is the area of triangle APB? The area of this triangle. So here we have already found out that AM equals to MB. AM equals to MB. So if we define AM as H, then MB will be also equal to H because they are equal to each other. And then we will focus on the right triangle, triangle AMQ, this right triangle. In the right triangle, triangle AMQ, sinus 60 degrees will be equal to H over 5. I'll repeat again. In the right triangle, triangle AMQ, sinus 60 degrees equals to H over 5. We will multiply this equation by 5, and we will get that H equals to 5 times sinus 60 degrees, and sinus 60 degrees is equal to 3 over 2. So we substitute sinus 60 degrees by square root of 3 over 2, and we will get that H equals to 5 times sinus 60 degrees is square root of 3 over 2. So we found out that H equals to 5 times square root of 3 over 2. And we want to find out the value of AB. AB equals to 2H. H plus H is 2H, so AB equals to 2H. AB equals to 2H. and A equals to 5 times square root of 3 over 2, so AB equals to 2 times h, that is 5 times square root of 3 over 2. So here 2 over 2 is 1. So we found out that AB equals to 5 times square root of 3 units. AB equals to 5 times square root of 3 units. PM, we have already found out that PM equals to 5 over 2. Five over 2 units. And the area of triangle APB, the area of triangle APB, that is actually equals to x. The area of triangle APB that equals to x will be equal to the base of the triangle that is AB times the I to the base that is PM over 2. I'll repeat again, x that equals to the area of triangle APB equals to the base of the triangle that is AB times the I that is PM over 2. But we have already found out that AB equals to 5 times square root of 3 units, PM equals to 5 over 2. So in conclusion, we found out that x that equals to the area of triangle APB equals to 5 times 5 is 25 times square root of 3, and or it is AB times PM over 2, so we have to divide it. This AB is 5 times square root of 3, PM is 5 over 2, and we have to divide all by 2. So here we have 5 times 5 is 25, 25 times square root of 3, and 2 times 2 is 4. So in conclusion, we found out that x that equals to the area of triangle APB, it is actually equals to 25 times square root of 3 over 4 square units. And the area of the green shape, equals to 2 times the area of segment APB that is to say it equals to 2 times the area of segment APB is 25 pi over 3 minus x that is to say it equals to 2 times 25 pi over 3, 25 pi over 4, 25 pi over 3 minus x. And x, we just right now found out that x equals to 25 times square root of 3 over 4. So here we'll take 25 out of those two expressions as a common factor, and we will get that the area of the green shape is equal to 2 times, and 25 was taken out as a common factor. So what is left from 25 pi over 3 after we took from it 25 as a common factor? What is left? It is actually pi over 3, and it is minus, and here we took 25 as a common factor, so what is left from minus 25 times square root of 3 over 4 after we took from it 25 as a common factor? What is left? It is actually square root of 3 over 4. So in conclusion, we found out that the area of the green shape equals to 2 times 25 pi over 3 minus square root of 3 over 4, and 2 times 25 is 50 times pi over 3 minus square root of 3 over 4. So we found out that the area of the green shape is equal to 50 times pi over 3 minus square root of 3 over 4 square units. Again, I'll repeat again, the area of the green shape equals to 50 times pi over 3 minus square root of 3 over 4 square units. Okay, so we finished with the first method. In the next step, I will present to you how to find out the area of this green shape according to the second method. And here we will define the center of this circle as point P, as we did in the first method. We will define the center of this circle as point Q. We define the first intersection point between those two circles as point A, and we will define the second intersection point between those two circles as point B. We join together points P and B, points B and Q, points A and Q and points A and P by straight line, as we did in the first method. We have already found out that all those line segments are equal to 5 units. They are the radiuses of those two circles. We join points P and Q by straight line. We have already found out that PQ is also equal to 5 units. So here we have triangle APQ is an equilateral triangle. Why? Because of all of its sides are equal to each other, and triangle PBQ is also an equilateral triangle because all of its sides they are equal to each other, they are equal to 5 units, and we know that in the equilateral triangle all the angles are equal to 60 degrees. So here all the angles of equilateral triangle APQ will be equal to 60 degrees. And here also in equilateral triangle PBQ all the angles will be equal to 60 degrees. can write down that the equilateral triangle APQ is congruent to the equilateral triangle PQB according to side rule. So I'll write it down. Triangle APQ is congruent to triangle PBQ according to side rule. All the sides of triangle APQ congruent to all the sides of triangle PBQ, and they are all equal to 5 units. And from the fact that those two equilateral triangles congruent to each other, we will conclude that they have also the same areas. So we can write down that the area of triangle APQ, is equal to the area of triangle PBQ. Why? Because they congruent to each other, therefore they have also the same areas. So what is the area of the green shape? The area of the green shape will be equal to the area of triangle APQ plus the area of triangle PBQ plus the areas of segment AP, segment PB, segment QB, and segment AQ. Okay, plus the area of segment AP plus the area of segment PB plus the area of segment QB plus the area of segment AQ. You can see it easily from the drawing that the area of the green shape equals to the area of triangle APQ plus the area of triangle PBQ plus the area of segment AP plus the area of segment PB plus the area of segment QB plus the area of segment AQ. Okay, I'll repeat again that the area of the green shape equals to the area of triangle APQ plus the area of triangle PBQ plus the area of segment AP plus the area of segment PB plus the area of segment QB plus the area of segment AQ. But because of the fact that the area of triangle APQ is equal to the area of triangle PBQ, we have already found out that the area of triangle APQ equals to the area of triangle PBQ. Therefore, we can substitute the area of triangle PBQ by the area of triangle APQ. Why? Because they are equal to each other. So I will write it down. And we get that the area of the green shape will be equal to the area of triangle APQ plus the area of triangle APQ, because the area of triangle PBQ equals to the area of triangle APQ, so we will substitute the area of triangle PPQ by the area of triangle APQ. Plus the area of segment AP plus the area of segment PB plus the area of segment QB plus the area of segment AQ. Okay. So the area of the green shape equals to the area of triangle APQ plus the area of triangle APQ, that is to say it equals to 2 times the area of triangle APQ plus segment AP, the area of segment AP plus the area of segment PB plus the area of segment QB plus the area of segment AQ. Okay, so we find out first of all the area of triangle APQ. What is the area of triangle APQ? Here we join points A and B together by a straight line. This is point M, as we did in the first method. We have already found out that AM, actually we have already found out that here AM, this is actually H, equals to 5 times square root of 3 over 2. This is H, and MB, that also equals to H, equals to 5 times square root of 3 over 2. Okay, so what is the area of triangle APQ? The area of triangle APQ will be equal to the base of the triangle, that is PQ, and we have already found out that PQ equals to 5 units, so it is the base of the triangle, that is PQ, times the height, that is H, over 2. I'll repeat again. The area of triangle APQ equals to the base of the triangle, that is PQ, times the height, that is H, over 2. And we have already found out that PQ equals to the base, PQ equals to 5 units, H equals to 5 times square root of 3 over 2, or divided by 2. So actually the area of triangle APQ equals to PQ, that is 5, times H, that is 5 times square root of 3 over 2, or divided by 2. So here 5 times 5 is 25, times square root of 3, and 2 times 2 is 4. So we found out that the area of triangle APQ equals to 25 times square root of 3 over 4 square units. Therefore, 2 times the area of triangle APQ will be equal to 2 times, and the area of triangle APQ is 25 times square root of 3 over 4. Okay? And what is the value, what is the area of segment AP? The area of segment AP the area of segment AP the area of segment AP equals to the area of sector AQP minus the area of triangle AQP. I'll repeat again. The area of segment AP equals to the area of sector AQP minus the area of triangle AQP. What is the area of sector AQP? The area of sector AQP equals to pi r squared times 60 degrees over 360 degrees. I'll repeat again. The area of sector AQP equals to pi r squared times 60 degrees over 360 degrees. And we already found out that the area of triangle AQP equals to 25 times square root of 3 over 4. So here r equals to 5, so r squared is 5 squared. 5 squared is 25, so here we will have 25 pi in the numerator, and 60 degrees over 360 degrees is 1 over 6, so in the denominator we have 6 minus 25 times square root of 3 over 4 square units. So we actually found out that the area of segment AP equals to 25 pi over 6 minus 25 times square root of 3 over 4 square units. So we have also to find out the area of sector PB. What is the area of sector PB? The area of sector PB, here this sector, the area, it is actually segment PB. Okay, we are talking about segment PB. This is segment PB. So the area of segment PB will be equal to the area of sector PQB minus the area of triangle PQB. I repeat again, the area of segment PB, this segment, equals to the area of sector PQB minus the area of triangle PQB. The area of sector PQB equals to pi r squared times 60 degrees over 360 degrees. I'll repeat again. The area of sector PQB equals to pi r squared times 60 degrees over 360 degrees. What is the area of triangle PQB? The area of triangle PQB equals to the area of triangle APQ. And we have already found out that the area of triangle APQ equals to 25 times square root of 3 over 4. Okay? The area of triangle PBQ equals to the area of triangle APQ, and we have already found out that the area of triangle APQ equals to 25 times square root of 3 over 4. So in conclusion, we found out that the area of segment PB equals to this expression. Here r equals to 5, so r squared is 25. So in the numerator we will have 25 pi, and in the denominator we have 60 over 360 is 1 over 6 minus 25 times square root of 3 over 4. So we actually found out that the area of segment PB equals to 25 pi over 6 minus 25 times square root of 3 over 4 square units, and it is exactly also the area of segment AP, that is also equals to 25 pi over 6 minus 25 square root of 3 over 4. So it equals to the area of segment AP. Again, the area of segment AP equals to the area of segment PB, and if we continue to calculate the area of segment QB and the area of segment AQ, we will arrive to the same result. They will be equal. The area of segment PQ, the area of segment BQ and segment AQ will be equal to this expression. That is to say, they will be equal to the area of segment PB and the area of segment AP. Therefore, we can multiply the area of segment AP by 4, and we will get the area of the 4 segments. So, in conclusion, the area of the green shape will be equal to 2 times the area of triangle APQ plus 4 times the area of segment AP. I'll repeat again, the area of the green shape will be equal to 2 times the area of triangle APQ plus 4 times the area of segment AP. And we have already found out that the area of triangle APQ equals to 25 times square root of 3 over 4 plus 4 times the area of segment AP, and we already found out that the area of segment AP equals to 25 pi over 6 minus 25 square root of 3 over 4 . So this expression equals to the area of the green shape. Here 2 times here 2 times 25 is 50 times square root of 3 over 4 plus 4 times 25 is 100, so it is 100 pi over 6 plus 2 times minus 25 is minus 100 times square root of 3 over 4. This expression is the area of the green shape. So here 50 minus 100, 50 times square root of 3 minus 100 times square root of 50 times square root of 3 over 4 minus 100 times square root of 3 over 4 is minus 50 times square root of 3 over 4, and here 100 pi over 6, we divide both the numerator and the denominator by 2, and we get that 100 over 2 is 50 and 6 over 2 is 3, all multiplied by pi. So here we'll take out 50 as a common factor of those two expressions, and we will get that, so 50 was taken out as a common factor of those two expressions. So what is left from 50 pi over 3 after we took from it 50 is a common factor? What is left? It is actually pi over 3, and what is left from minus 50 times square root of 3 over 4 after we took from it 50 is a common factor? What is left from it is actually square root of 3 over 4. So we found out that the area of the green shape equals to 50 times pi over 3 minus square root of 3 over 4 square units, exactly as we found in the first method. In the next step, I will summarize the lecture. So here we have two circles. Each circle is passing through the center of the other circle. The radius of each circle equals to 5 units, and we want to find out the area of this green shape. So first of all, I presented to you the definition of a sector. A sector is actually the area inside a circle that is bounded by two radiuses, and the arc that is between those two radiuses, and the area of a sector is equal to pi r squared times the angle that is between the two reduces over 360 degrees. In this case, the angle between the two reduces is 60 degrees. So the area of this specific sector will be equal to pi r square over 60 degrees over 360 degrees, when r equals to the radius of this circle. Okay, so that is the definition of a sector, and I repeat again that the area of any sector is equal to pi r square times the angle between the two radiuses over 360 degrees, when r is equal to the radius of the circle. Okay, so then I presented to you the definition of a sector. I presented to you the definition of a segment. Here, segment is the area that is bounded by chord and by the arc that is attached to that chord inside the circle. Again, in this case, segment AB is the area that is bounded by chord AB and arc AB. Okay, this is actually the green area, and the formula for the area of a segment, it is actually equals to the area of sector AOB minus the area of triangle AOB. You can see it easily from the drawing that if you subtract the area of triangle AOB from the area of sector AOB, you will get exactly the area of segment AB. Okay? Then we define the center of this circle as point P. We define the center of this circle as point Q. We define the first intersection point between those two circles as point A, and we define the second intersection point between those two circles as point B. We join together points A and P, points P and B, points B and Q, points N and Q. Here, QB is the radius of this circle. Why? Because it starts from the center of this circle, that is to say from point Q, and ends at point B, that is a point on this circle itself. Therefore, it is the radius of this circle, that is to say it equals to 5 units. The same thing is true for the other segments. They are all equal to 5 units because they are the radiuses of those two circles. And here we created rhombus APBQ, and the definition of a rhombus is the quadrilateral that has 4 equal sides but not 4 right angles. Any quadrilateral that has 4 equal sides but not 4 right angles is defined as a rhombus. So here, quadrilateral AQPB is a rhombus. Then we join together points A and B by straight line. AB is the first diagonal of rhombus APBQ. We join together points P and Q by straight line. PQ is the second diagonal of rhombus APBQ. We define the intersection point between AB and PQ as point M. The diagonals of a rhombus has 2 characteristics. Here, I wrote them down here. The characteristics of the diagonals of a rhombus is that, first of all, they are perpendicular to each other. Here, diagonal AB perpendicular to diagonal AQ, to diagonal PQ, and diagonal PQ is perpendicular to diagonal AB. That is to say, we have here 4 right angles. 1, 2, 3, 4. This is the first characteristic of a rhombus. And the second characteristic of a rhombus is that the diagonal, actually the second characteristic of the diagonals of a rhombus is that the diagonals of a rhombus bisect each other. That is to say, diagonal AB bisect PQ. That is to say, PM equals to MQ. And also diagonal PQ bisect diagonal AB. That is to say, AM equals to MB. Okay, then we focus on those 4 right triangles, and on those 4 angles. Here we can say that the cosine of those 4 angles is equal to 5 over 2 over 5. The cosine of this angle equals to 5 over 2 over 5, and the cosine of this angle equals to 5 over 2 over 5. The cosine of this angle equals to 5 over 2 over 5, and the cosine of this angle is also equal to 5 over 2 over 5. And 5 over 2 over 5 is 1 over 2. And when the cosine of any angle equals to 1 over 2, it means that the angle itself equals to 60 degrees. So we found out that all 4 angles here are equal to 60 degrees. Then we proved that those 2 triangles can go into each other. Triangle APB can go into triangle AQB. Why? Because AP equals to AQ equals to 5 units, AP equals to AQ equals to 5 units, PB equals to BQ equals to 5 units, and AB equals to itself. It is a common side that belongs to both triangles. So we proved that triangle APB can go into triangle AQB according to side rule. And from the fact that those 2 triangles can go into each other, we will conclude that they have also the same areas. That is to say, the area of triangle APB is equal to the area of triangle AQB. Okay? And then, what is the area of sector APB? The area of this sector equals to pi r squared times 120 degrees over 360 degrees. Okay? The area of sector APB equals to pi r squared times 120 degrees over 360 degrees. Here we concluded that the area of triangle APB is equal to the area of triangle AQB, and we defined the areas of those 2 triangles that are equal to each other as x. Okay, and here pi r squared, r is 5, so r squared is 5 squared, 5 squared is 25. So in the numerator we have 25 pi, and in the denominator we have 120 degrees over 360 degrees is 1 over 3. So in the denominator we have 3. So in conclusion, we found out that the area of sector APB equals to 25 pi over 3 square units. Likewise, we calculated the area of sector AQB. The area of sector AQB will be equal to pi r squared times 120 degrees over 360 degrees. The area of sector AQB equals to pi r squared times 120 degrees over 360 degrees. Here it is the same calculation as we did here, so it is equal to 25 pi over 3. So we found out that the area of sector AQB equals to the area of sector APB. Why? Because both areas are equal to 25 pi over 3. Okay? The area of sector APB is equal to the area of sector AQB. And we have already found out that the area of triangle APB is equal to the area of triangle AQB. Okay? The area of triangle APB is equal to the area of triangle AQB, and they are equal to x according to our definition. And what is the area of segment APB? The area of segment APB will be equal to the area of sector APB minus the area of triangle APB. Again, the area of sector APB equals to the area of segment APB equals to the area of sector AQB minus the area of triangle AQB. We have already found out that the area of sector AQB equals to 25 pi over 3, and the area of triangle AQB equals to x according to our definition. So in conclusion, we found out that the area of segment APB equals to 25 pi over 3 minus x square units. Okay? And then we actually calculated the area of segment AQB. The area of segment AQB is equal to the area of sector APB minus the area of triangle APB. Okay, so the area of sector APB equals to 25 pi over 3 minus x. Okay, and then we calculated the area of sector of segment AQB. Here actually we found out that the area of segment APB is equal to the area of segment AQB. Why? Because both areas are equal to 25 pi over 3 minus x. Okay? Why? Because the area of segment AQB equals to the area of sector APB, that is actually 25 pi over 3, and the area of triangle APB is x. So in conclusion, we found out that the area of triangle AQB equals the area of segment AQB equals to 25 pi over 3 minus x, exactly as the area of segment APB. Therefore, we actually can conclude that the area of segment APB is equal to the area of segment AQB. Okay, here the area of segment APB equals to the area of segment AQB, and both areas are equal to 25 pi over 3 minus x square units. And what is the area of the green shape? The area of the green shape equals to the area of segment APB plus the area of segment AQB. The area of the green shape equals to the area of segment APB plus the area of segment AQB. The area of segment APB plus the area of segment AQB. But because of the fact that the area of segment APB equals to the area of segment AQB, we can substitute the area of segment AQB by the area of segment APB. We did it, and we got that the area of the green shape equals to the area of segment APB plus the area of segment APB. That is to say, the area of the green shape equals to 2 times the area of segment APB. And the area of segment APB, we have already found out that it is equal to 25 pi over 3 minus x. So 2 times the area of segment APB will be equal to 2 times 25 pi over 3 minus x. So the only thing that is left to find out in order to find out the area of the green shape is to find out the value of x, that is actually the area of triangle APB, and it is also the area of triangle AQB. So we'll find out the area of triangle APB the area of triangle APB. Here we focus, so the area of this triangle equals to the base of the triangle times the height over 2. So we have to find out the value of AB. But we know that AM equals to MB, so if AM equals to H, then MB will be also equal to H. So here, sinus 60 degrees will be equal to H over 5. Sinus 60 degrees equals to H over 5. So H, we will multiply this equation by 5, and we will get that H equals to 5 times sinus 60 degrees. And sinus 60 degrees equals to square root of 3 over 2. So H equals to 5 times square root of 3 over 2. But AB equals to H plus H. AB equals to 2H. So AB equals to 2 times H, and H is 5 times square root of 3 over 2. So here 2 over 2 is 1. So we found out that AB equals to 5 times square root of 3 units, and PM, the height PM equals to 5 over 2. And therefore, X, that is the area of triangle APB, is equal to the base AB times the height PM over 2. The area of triangle APB, that is X, equals to the base AB times PM over 2. AB equals to 5 times square root of 3 over 2. And PM equals to 5, actually AB equals to 5 times square root of 3, and PM equals to 5 over 2. So, and we have to divide it by 2, so it is actually 5 times square root of 3 over 2 times 5 over 2. 5 times 5 is 25, so in the numerator we have 25 times square root of 3, and in the denominator we have 2 times 2, that is 4. So in conclusion, we found out that the area of triangle APB, that is actually X, is equal to 25 times square root of 3 over 4 square units. Okay, so the area of the green shape equals to 2 times the area of segment APB. And so that is to say it equals to 2 times 25 pi over 3 minus X. And we have already found out that X equals to 25 times square root of 3 over 4, so we'll substitute X by 25 times square root of 3 over 4, we did it, and we got that the area of the green shape equals to 2 times 25 pi over 3 minus 25 times square root of 3 over 4. Here we took 25 as a common factor out of those two expressions, and we got that the area of the green shape equals to 2 times 25 pi over 3 minus square root of 3 over 4. 2 times 25 is 50. So we found out that the area of the green shape, according to the first method, equals to 50 times pi over 3 minus square root of 3 over 4 square units. We finished with the first method. Then I presented to you how to find out the area of the green shape according to the second method. In the second method, we did the same construction as we did in the first method, and here triangle APQ is an equilateral triangle. That is to say, all of its sides are equal to each other, and triangle PBQ is also an equilateral triangle. And those two equilateral triangles can go into each other according to side rule. So triangle APQ can go into triangle ABQ according to side rule. And from the fact that those two equilateral triangles can go into each other, we will conclude that they also have the same areas. That is to say, the area of the equilateral triangle APQ equals to the area of the equilateral triangle PBQ. Okay? Then, what is the area of the green shape? the area of the green shape equals to the area of triangle APQ plus the area of triangle PPQ plus the area of segment AP plus the area of segment PB plus the area of segment BQ plus the area of segment AQ. Okay, again, the area of the green shape equals to the area of triangle APQ plus the area of triangle PBQ plus the areas of segments AP, PB, BQ, and AQ. But because of the fact that the area of triangle APQ is equal to the area of triangle PBQ, we can substitute the area of triangle PBQ by the area of triangle APQ because they are equal to each other. So we get that the area of the green shape equals to the area of triangle APQ plus the area of triangle APQ plus the area of the four segments. So the area of the green shape equals to 2 times the area of triangle APQ plus the area of the four segments. And the area the area of triangle APQ is equal to, we have already found out that the area of triangle APQ equals to 25 times square root of 3 over 4. Here we did the calculation for the area of triangle APQ. The area of triangle APQ, here the area of triangle APQ equals to the base of the triangle that is PQ times the height that is AM over 2. Again, the base PQ times the height H over 2. PQ equals to 5. H equals to 5 times square root of 3 over 2, all divided by 2. So the area of triangle APQ equals to 5 times 5 is 25. So in the numerator we have 25 times square root of 3. And in the denominator we have 2 times 2, that is 4. In conclusion, we found out that the area of triangle APQ equals to 25 times square root of 3 over 4. So here we can put the value of the area of triangle APQ, that is actually 25 times square root of 3 over 4. And so we found out the area of 2 times the area of triangle APQ, and we also have to find out the area of segment AP. The area of segment AP equals to the area of sector AQP minus the area of triangle AQP. Here, the area of segment AP equals to the area of sector AQP minus the area of triangle AQP. Okay, and the area of sector AQP is pi r squared times 60 degrees over 360 degrees. And the area of triangle AQP, we have already found out that it is equal to 25 times square root of 3 over 4. So here r equals to 5, so r square is 5 square, 5 square is 25, so in the numerator we have 25 pi, and in the denominator we have 60 over 360 is 1 over 6, so in the denominator we have 6. So in conclusion, we found out that the area of segment AP equals to 25 pi over 6 minus 25 times square root of 3 over 4. Then we have also to, after we found out the area of segment AP, we have to find out the area of segment PB. And the area of segment PB equals to the area of sector PQB minus the area of triangle PQB. Again, the area of this segment PB equals to the area of sector QBP minus the area of triangle QBP. And the area of sector PQB equals to pi r squared minus 60 degrees over 360 degrees. And the area of triangle PQB is equal to the area of triangle AQP. Here, the area of triangle APQ is equal to the area of triangle PBQ. And we have already found out that the area of triangle APQ equals to 25 times square root of 3 over 4. So in conclusion, we found out that the area of segment PB equals to 25 pi over 6 minus 25 times square root of 3 over 4. Exactly as the area of segment AP. That is to say, the area of segment PB equals to the area of segment AP, and it equals to this expression. And if we continue to calculate the areas of segment AQ and BQ, we will arrive to the same result, that it is actually equals to the area of segment AP. Therefore, we can multiply the area of segment AP by 4, and in this way we get the areas of the 4 segments in total. Therefore, here the area of the green shape will be equal to 2 times the area of triangle APQ plus 4 times the area of segment AP. And we have already found out that the area of triangle APQ is equal to 25 times square root of 3 over 4 square units. So we multiply it by 2, and we also have to add the 4 times the area of segment AP. And the area of segment AP equals to 25 pi over 6 minus 25 square root of 3 over 4. So here 2 times 25 is 50, 4 times 25 is 100, and 4 times minus 25 is minus 50. So in conclusion, we found out that the area of the green shape equals to 50 times square root of 3 over 4 plus 100 pi over 6 minus 100 times square root of 3 over 4. Here we have 50 times, actually 50 times square root of 3 over 4 minus 100 times square root of 3 over 4 equals to minus 50 square root of 3 over 4. And here, this expression 100 pi over 6, we divided both the numerator and the denominator by 2, and we got that 100 over 2 is 50, and 6 over 2 is 3. So in conclusion, we found out that the area of the green shape equals to 50 pi over 3 minus 50 times square root of 3 over 4. We took 50 as a common factor out of those two expressions. And here, what is left from 50 pi over 3 after we took from it 50 as a common factor? What is left? It is actually pi over 3. And what is left from minus 50 times square root of 3 over 4 after we took from it 50? What is left? It is actually square root of 3 over 4. So in conclusion, we found out that the area of the green shape equals to 50 times pi over 3 minus square root of 3 over 4 square units, exactly as we found out in the first method. Okay, thank you very much.